Change of variables, or substitution. We first need to talk a bit about differentials, which are closely related to derivatives. Let y equal f of x. Then we define the differential dy by dy equals f prime of x times dx, or dy dx times dx. Notice that this is defined in such a way that it appears that the dx is canceling out, leaving dy. Let's look at a few examples. In each case, we'll look at an equation defining a dependent variable y in terms of an independent variable x, and then the associated derivative in the differential. Suppose that y equals x cubed. Our derivative there is dy dx equals 3x squared, and so the differential dy is 3x squared dx. Suppose that u is equal to cosine t. Our derivative is du dt equals minus sine t, and so du is equal to minus sine t times dt. If x is equal to tangent theta, then dx d theta is secant squared theta, and dx is secant squared theta times d theta. If w is the square root of x squared plus 1, then dw dx is equal to 1 over 2 times the square root of x squared plus 1. By the chain rule, we multiply by the derivative of x squared plus 1, or 2x. Notice that the 2's go away, leaving x over the square root of x squared plus 1. So, the differential dw is equal to x over the square root of x squared plus 1 times dx. Old formulas in terms of differentials. Each property of the derivative has a direct analog for differentials. Recall the linearity properties of the derivative. First, the derivative of sum u plus v is equal to the sum of the derivatives. By multiplying both sides of this equation by dx, we have essentially the same rule for differentials. The differential of u plus v is equal to du plus dv. The other linearity property of derivatives is that the derivative of constant times the function u with respect to x is equal to the constant c times du dx. The analogous property of differentials is that the differential of c times u is equal to c times the differential of u, provided, of course, c is a constant. The product rule. Product rule for derivatives says that the derivative with respect to x of u times v is u times the derivative of v plus v times the derivative of u. Product rule for differentials says essentially the same thing about differentials. The differential of u times v is equal to u times dv plus v times du. Likewise, the quotient rule says that the derivative with respect to x of u divided by v is equal to the derivative of u times v minus u times the derivative of v divided by v squared. The version of this for differential says that the differential of u divided by v is equal to v times du minus u times dv divided by v squared. Now let's look at the chain rule. The derivative with respect to x of f of u is f prime of u times du dx. For differentials, the chain rule says that the differential of f of u is f prime of u times du. Notice this is essentially just the definition of the differential. Anti-differentiation. The indefinite integral of capital F prime of x dx equals capital F of x plus c. Notice that we can think of capital F prime of x dx as the differential dy of y equals capital F of x. So an equivalent statement is that the indefinite integral of dy equals y plus an arbitrary constant c. Change of variables, or the u substitution. The simplest change of variables involves integrands of the form f of u of x times u prime of x. Here we can consider u prime of x times dx to be the differential of the variable u, and then the other factor we simply think of as f of u. So the integral is transformed into simply the integral of f of u du. This formula is sometimes called the reverse chain rule. since it applies to integrands that have the form that results from applying the chain rule for differentiation. Now let's look at a couple of examples. Consider the integral of x squared plus 1 quantity cubed times 2x dx. Notice that we can think of x squared plus 1 cubed as u cubed, where u is equal to x squared plus 1, and so du is equal to 2x dx. And so we can transform this into the integral of u cubed du. The power rule now gives us 1/4 of u to the 4th plus c. And now finally we simply go back and replace u with x squared plus 1, and we have our desired antiderivative. Here's another example. Notice that it's the same as the previous example except without the factor of 2. Now let's suppose that we've encountered this problem and we'd like to approach it by making a substitution. We want to substitute u equals x squared plus 1 just as before. Notice that du is 2x dx. Of course, x squared plus 1 cubed will be replaced by u cubed, but we need to know what to put in place of x dx. That's not exactly du, but it's 1/2 of du. So our integral becomes the integral of u cubed times 1/2 du. We can pull the 1/2 factor out front of the integral, integrate to get 1/8 of u to the 4th plus c, and then replace u with x squared plus 1 for our final answer. Now let's look at some more examples. Consider the indefinite integral of the square root of 3x plus 2 times dx. Here we have a composition where the inside function is 3x plus 2. So this suggests that we substitute u equals 3x plus 2. So now the question is, what do we write in place of dx? We have du equals 3 times dx, which tells us that dx is 1/3 of du. So our integral becomes that of the square root of u times 1/3 du. And of course we can bring the 1/3 outside the integral, and so we only have to antidifferentiate the square root function. So we get 1/3 times 2/3 u to the 3/2 power plus c by the power rule, which is 2/9 times 3x plus 2 to the 3/2 power plus c. Another example. The integral of x times the square root of x squared plus 1 dx. Notice that under the radical here we have the function x squared plus 1, whose differential is 2x dx. Now we don't have a factor of 2, but we do have a factor of x as well as the dx. So let's rearrange and group the x and the dx together. Now we're going to substitute u equals x squared plus 1, which tells us that du is 2x dx, and x dx is 1/2 of du, so our integral becomes the integral of the square root of u times 1/2 of du. Now we'll just bring the 1/2 outside, integrate the square root function, getting 1/2 of 2/3 u to the 3/2 plus c, and then replace u with x squared plus 1. So we have 1/3 x squared plus 1 to the 3/2 power plus c. Another example. Suppose we have the integral of the square root of 1 plus sine x times cosine x dx. Let's first notice that we have cosine x dx outside of the square root here, and that cosine x is precisely the derivative of what's under the square root, 1 plus sine x. So we'll substitute u equals 1 plus sine x, for which du is cosine x dx, and so our integral becomes simply the integral of the square root of u du. This is 2/3 of u to the 3/2 power plus c, and now we go back and replace u with 1 plus sine x for our final result. Another example. The integral of x squared divided by the square root of x cubed plus 1 dx. Now here let's notice that x squared dx is close to being the differential of the quantity that's inside of the square root in the denominator. So let's substitute u equals x cubed plus 1, calculating du equal to 3 times x squared dx. Dividing by 3 tells us that x squared dx is 1/3 of du. So our integral becomes the integral of 1 over the square root of u times 1/3 du, and we may as well go ahead and put the 1/3 outside the integral. 1 over the square root of u is u to the minus 1/2 power, so integrating gives us 1/3 times 2u to the plus 1/2 power plus c, and now replacing u with x cubed plus 1 gives us our final result, 2/3 times the square root of x cubed plus 1 plus c. Another example. The integral of x squared times the sine of x cubed plus 1 dx. Notice that we have x cubed plus 1 inside the sine function, and we also have a factor of x squared outside, so we should be able to do this by substituting for x cubed plus 1. So let's put the x squared beside the dx, and then substitute u equal to x cubed plus 1. That makes du 3x squared dx, which means that x squared dx is 1/3 of du. So our integral becomes 1/3 of the integral of sine u du. Since sine is the derivative of minus cosine, we now have minus 1/3 cosine u plus c, and finally we replace u with x cubed plus 1. Example. The integral of sine cubed times cosine x dx. Here one of the factors is a composition where sine x is the inside function and the cube function is on the outside. Fortunately, we have a factor cosine x dx, which is precisely the differential of sine x. So we'll substitute u equals sine x, which means du is cosine x dx, and transform our integral into the integral of u cubed du. So we get 1/4 of u to the 4th plus c, and finally replace u with sine x. 1/4 of sine to the 4th x plus c. Example. The integral of tangent squared x times secant squared x dx. Let's recall that secant squared x is the derivative of tangent x. So we want to substitute u equals tangent x here, which gives us du equal to secant squared x dx. And so we have the integral of u squared du upon making our substitution. So we get 1/3 of u cubed plus c, and since u is tangent x, this becomes 1/3 of tangent cubed x plus c. Now here's a slightly different kind of example. Suppose we want to integrate the function x divided by x minus 1 cubed. What complicates matters most here is the fact that we have x minus 1 inside of the cube function in the denominator, as opposed to, say, simply x cubed. So what we can attempt to do here is substitute u equals x minus 1 in the hopes of obtaining a simpler integral. With u equals x minus 1, du is equal to dx, since the derivative of u with respect to x is 1. So in our integral, we'll replace the denominator with u cubed, replace dx with du, and now the issue is, what do we do about x? And this is what makes this example different. Notice that the factor x is not covered by du here. Since we did not get it from du, we have to go back to the original substitution, u equals x minus 1, and solve for x. X is u plus 1, so that's what we substitute for x in the numerator. So now the question is, are we any better off? Well, we are, because we can now split up the integrand into two terms, each of which is a power of u. It's u to the minus 2 power plus u to the minus 3 power. Now each term is easy to integrate with the power rule. Our first term is u to the minus 1 divided by minus 1. The second term becomes u to the minus 2 divided by minus 2, and we add our constant c. Now before we substitute back in terms of x, let's do a little simplification here. Let's notice that our two terms are essentially fractions with a common denominator of 2u squared. The numerator is then minus 2u minus 1. Now let's go back and replace u with x minus 1, and notice that we can simplify our numerator here. It's equal to minus 2x plus 2 minus 1, or 1 minus 2x, and so we have 1 minus 2x divided by 2 times x minus 1 squared plus c. Definite integrals. The basic substitution rule for definite integrals is as follows. The integral from a to b of f of u of x times u prime of x dx is equal to the integral from u of a to u of b of f of u du. The point here is that when making a u substitution in a definite integral, the limits of integration must be transformed from values of x to values of u. Example. Let's compute the integral from 0 to 2 of x squared over the square root of x cubed plus 1 dx. We'll make the substitution u equals x cubed plus 1, computing du equals 3x squared dx, and noting that x squared dx is 1/3 of du. And so our substitution gives us 1/3 the integral of 1 over the square root of u du, with limits u of 0 to u of 2. When x is 0, u is equal to 1, and when x is 2, u is equal to 9. So we have 1/3 the integral from 1 to 9 of 1 over the square root of u du. Now applying the power rule to u to the minus 1/2 power, we get 1/3 times 2 times u to the 1/2 power, or 2/3 times the square root of u, evaluated from 1 to 9. So we simply do the evaluation here and obtain 2/3 times 3 minus 1 equals 4/3. Notice that by changing the limits of integration, we were able to do our evaluation in terms of u, which allowed us to avoid the step of going back to the x variable. Another example. The integral from 0 to pi over 2 of sine cubed x times cosine x dx. Here the substitution that we want to make is u equals sine x, which gives us du equals cosine x dx, and so our integrand becomes u cubed times du, and our limits of integration are u of 0 to u of pi over 2. When x is 0, u is equal to sine of 0, which is 0, and when x is pi over 2, u is equal to the sine of pi over 2, which is 1, and so our integral is that of u cubed du from 0 to 1. So we have 1/4 u to the 4th evaluated from 0 to 1, which of course gives us 1/4 times 1 minus 0, or 1/4. Another example. The integral from 0 to 1 of x plus 1 times the square root of 1 minus x squared dx. Here we need to break our problem into two pieces, writing it as the integral from 0 to 1 of x times the square root of 1 minus x squared dx, plus the integral from 0 to 1 of 1 times the square root of 1 minus x squared dx. This is because we need to treat each of these two integrands in different ways. The first term, the integral from 0 to 1 of x times the square root of 1 minus x squared dx, we'll do by substitution u equals 1 minus x squared, for which du is minus 2x dx. So x dx is minus 1/2 du. So our transformed integral looks like minus 1/2 the integral of the square root of u du, and now we fill in our transformed limits of integration. When x is 0, u is 1, and when x is 1, notice that u is 0. Notice that we're integrating here from right to left, but since we have a minus sign out front, we may as well absorb that minus sign into the integral by reversing the limits of integration, writing positive 1/2 times the integral from 0 to 1 of the square root of u du. So now we anti-differentiate, obtaining 1/2 of 2/3 u to the 3/2 power, which will evaluate from 0 to 1, obtaining 1/3 times 1 minus 0. Now for the second term, a simple u substitution is not going to be successful. The reason for that is that the quantity under the radical there has the differential minus 2x dx, but there is no x factor outside of the square root. So if we try the same substitution as we did on the first term, things are only going to get far more complicated. It turns out that it's very easy to evaluate this integral geometrically. This is the integral from 0 to 1 of the square root of 1 minus x squared, a function whose graph is just the top half of the unit circle. Since we're integrating from 0 to 1, we're going to get the area underneath that semicircle between 0 and 1, which is just going to be 1/4 of the total area of the full unit circle, which is pi over 4. So by adding our first and second terms here, we have 1/3 plus pi over 4 for the value of our original integral. Notice that over a common denominator of 12, we could write this as 4 plus 3 pi over 12.